Hello everyone, welcome to this online course on material science. This is lecture 1 in module 2 and the central topic of discussion is superconductivity. For this lecture, I will use this classic textbook from James Annett, published by Oxford University Press, and the book has the title Superconductivity, Superfluids and Condensates. To begin, let me tell you this, that the superconductivity was discovered around 1911 by Kamerlingh Onnes. But just to put you in the context, let me give you some additional information that if you remember that around 1897, Thomson discovered the electron, right? So electron was discovered by Thomson, right? And then around 1900, recall that Drude proposed his model, and in Drude model he tried to explain different measurable quantities like electrical conductivity, thermal conductivity in terms of a simple model including the electrons inside the solid, right? So Drude model was proposed in 1900, and then kind of you can see during that time around 1911 Kamerlingh Onnes he was trying to verify the Drude model for different materials at low temperature. That's the key. At low temperature, let's say in few Kelvin. So somehow, let me tell you this information that he kind of liquefied the helium and then build different cryostat where he can really reach a low temperature, let's say 2 or 3 Kelvin. And then he was trying to understand whether the Drude model can be explained at that low temperature. He was testing the conductivity or the resistivity of different materials and then trying to understand whether Drude model holds at very low temperature, right? That was his plan. He was trying to measure different materials. And let's say he started with gold, right? And then he went to a very low temperature and he kind of measured the resistivity of the sample, right? And then what was his expectation? That's the important thing, is that if you follow this curve here, so he was measuring, let's say, the temperature and the resistivity of the sample. So rho here is nothing but the resistivity of the sample. So he was cooling down the sample and measuring the resistivity. So what was the expectation at very low temperature is that the resistivity will decrease as you decrease the temperature, and then when you really close to the absolute zero, it will saturate to some fixed value, right? And that's the value which is independent of temperature. So that's the expectation from a model using Drude. I will show you later in this lecture that how this Drude model explains this sort of behavior at low temperature. But for the moment, let's assume you know this information, that the resistivity of some material should follow this sort of a line and then will saturate at some point. And then the question is, for the gold, he kind of measured behavior like this, that the resistivity was going down and then it has a tendency to look like it's flattening out at some point low temperature. But then, as I have mentioned, that he was trying different materials, right? So the next material maybe he took was the mercury, and you can see the mercury, and then a dramatic incident occurred, right? What happened is that as he was trying to measure the resistivity of the sample, and then at some temperature, let's say Tc, and Tc is nothing but, C stands for the critical temperature. Let's say there is some critical temperature for this mercury, and then what happened is that below that temperature, the resistivity of the sample was exactly 0. That was really a surprise, because the Drude model was suggesting it will saturate to some or it will kind of go to a fixed value, non-zero resistivity. But what was measured is that below certain temperature, the critical temperature, the resistivity of the sample was exactly 0. That was really a surprising, very, very surprising phenomena, because you can see beyond this, below this TC, you cannot measure any resistivity of the sample. It is as though the sample has 0 resistivity, right? So in this region below TC, you can see what's happening is that the resistivity of the sample is 0, which kind of imply that the conductivity, right? Resistivity is nothing, conductivity is nothing but the inverse of the resistivity. So if the resistivity is 0 for some sample, it's implying 1 by 0, the conductivity is kind of infinite, right? So whatever happening in this temperature range, the sample has infinite conductivity. And that's how the superconductor was discovered, that below a certain temperature, certain materials has a vanishing resistivity. It means infinite conductivity. And below that temperature, the materials kind of become resistanceless, right? And that's why the name was given superconductor, because it conducts really well, because it has an infinite conductivity. That's the context in which superconductivity, the name is given to this kind of materials. But later we will see that this infinite conductivity or 0 resistivity is not really the fundamental requirement for a superconductivity. I'm just giving you this information, but I will explain it later at some point, that although the discovery of superconductivity occurred in such a way that it kind of telling you that yes, the material, those are superconductor, has this unique property that the conductivity is going infinite, or resistivity is going down and going to 0. But you will see that's not the only unique property for superconductivity. Okay, and let me give you a list of superconductors. You can see all aluminum we have, then we have mercury, we have niobium, all those titanium, then we have all kind of different elements, right? And here you can see for every superconductor, the important parameter is that this critical temperature below which the sample becomes superconductor. So if somebody asks you what is this critical temperature, if you are at some temperature which is bigger than this critical temperature, then the material is normal. Normal means it's not superconducting. So that's the normal state of the material. So normal state, sometimes I would write it at NS. But as soon as you go below TC, what happens? The superconducting state kicks in and the sample becomes superconductor. And that's kind of SC. And you can see that every superconducting material is defined or characterized by a critical temperature below which the material becomes superconducting, and above which it stays a normal matter, right? And you can see there are some elements, and then we have also some complex materials like you can see that particularly this one has a critical temperature of 135 to 165 Kelvin, right? So it's really high. Although the elements that we are using, for example, the mercury was 4.11, for niobium this is 9.3 Kelvin, and you can see that among the elements, right, 9.3 is the highest. So niobium has the highest TC. And why I am telling this? Because you can see here we have 92 degrees Celsius, 92 degree Kelvin. Here we have 135 to 165 Kelvin. Why this is important? Because people are looking for materials that has a high super transition temperature, right, or the high critical temperature. And the reason is that it is really difficult to cool things at like around 1 or 2 Kelvin, right? Because you need some specialized cryostat. You need liquid helium. Sometimes you will use liquid helium 3 and 4 in combination of those two to make lower your temperature. So it's expensive to cool things down, right? That's always the case because you're using helium, and helium is expensive to buy, the liquid helium. Now, if you can reach somewhere, let's say 92 Kelvin, the important thing to remember is that nitrogen, the boiling temperature of nitrogen is 77 Kelvin, right? So if you just put this sample in a liquid nitrogen, it will just superconduct. And look at the internet, the cost of the helium-4 and the cost of the nitrogen. Nitrogen is very cheap. So in the commercial use, right, you need something to be less expensive. So in that sense, there is a tremendous effort to make different kind of new superconductor which has a very high TC, and the ultimate goal is to make a superconductor that will superconduct at room temperature, right? And then that will be a big breakthrough if you can make a material superconduct at 300 Kelvin. Then you don't need in this low temperature systems. It's expensive like the cryogens for cooling your devices, right? So that's an important aspect of superconductivity, that we want them to have high TC as possible so that we can easily make them superconduct. And we will see what's the consequence of this zero resistivity or infinite conductivity. We will see them in the lectures to come, but let me just make another few points, is that the gold and what are the best conductors in room temperature. If you ask yourself that, let's talk about some good conductors, right? No doubt we have copper, we have gold, right? Those are really good conductors. And then you have a natural tendency to ask yourself, okay, if something really good conducts well at room temperature, it should be easy to make them superconducting, right? Because they're already conduct so well in room temperature. What's preventing them to be superconducting, right? But surprisingly, it turns out that these good conductors like copper and gold, they really don't superconduct, right? But instead, we have aluminum, lead, tin, which are like less conduct in room temperature, but they are really a superconducting material. That's another really puzzling thing, is that why, at a first view, that why these good conductors, right, the best conductors are not superconducting, but the materials which have a conductivity, I would say, not as good as copper or gold, they really superconduct at low temperature. That's another puzzling thing in this first lecture, right? And to give you that why this was like a tremendous surprise to Kamerlingh Onnes, right? Because he was expecting the resistivity to go to a fixed value at low temperature. And for that, let me introduce a slight bit of, you have already seen this Drude model, but we need to revisit that Drude model to understand why you expect, if some material follows the Drude model, the resistivity cannot be zero for certain materials, right? And for that, you recall, let me just write down some basic equation from your study of electromagnetism, is that the current density J is nothing but the conductivity times the applied electric field, right? So this is the relation between the current density J and the applied electric field. And from that, you can see that then the electric field is nothing by 1 by the conductivity times J, right? These are very useful relation back in when you're studying the Ohm's law. And 1 by sigma is nothing but the resistivity. So that's how you relate your applied electric field with the current density of the sample, right? Now, if you recall in the Drude model, the parameter that we estimate was this resistivity, and it was given for a sample by the mass of the electron divided by the density of electrons, which is n, then the charge of the electron squared, then we have some parameter 1 by tau. And this was a phenomenological parameter in the Drude model, and what tau was is nothing but the scattering time, or time between two scattering events of electrons when it moves inside the solid, right? So our Model is that we have a number of electrons, and when electron moves, electron will scatter off, and then it will change its direction, and this tau is the time between two scattering events, right? So that's scattering time, and 1 by tau is nothing but, so if this is scattering time, then 1 by tau is the relaxation, or sorry, the scattering rate, because if something scatters more frequently, then tau will be small, right? It's the time between two scattering events. Then 1 by tau will be a big number, so scattering rate will be high. So 1 by tau is nothing but the scattering rate of electron inside a solid. Scattering rate, how often electron scatters with each other. That's really the simple Drude model. Now you can estimate this 1 by tau, and if you ask yourself, okay, inside a solid, what are the different things that we have? We have electrons, we have ions, and we have impurities, right? So the first thing to ask is that this scattering can happen between electron and electron, right? That's electron scattering. So this is nothing but electron scattering, and you denoted that by 1 by tau, the scattering rate between electron and electron, right? And you can show that this is temperature dependent, and it goes as the square of the temperature. So the electron scattering rate is proportional to the temperature squared. Now, what about the impurity? In a piece of solid, you might have different impurities, and electron will scatter off these impurities. And so the impurity scattering rate let me denote that by 1 by tau electron scatters from impurity. So that's the subscript IMP for the impurity. And this is independent of temperature. That's another finding, independent of T. So we have the last one, which is the scattering between the electron and the ions. And from your basic second year solid state physics, you recall that the ions, the movement of ions are nothing but the phonons, right? So when I say the scattering of electron with the lattice or with the ions, it means electron-phonon interaction, right? Or electron-phonon scattering. So you can also model this electron-phonon scattering rate, right? And from that you can show that the scattering rate between the electron, EL, and pH for phonon goes as the 5th power of the temperature, and this is true for when temperature is less than the Debye temperature, right? And for every material you can define a Debye temperature, and these things I have discussed in lectures of like the how you model the phonons and how do you model the energy of the specific heat in the materials, right? So from that, recall there was a TD temperature, which is known as the Debye temperature, and this model is saying if you are below this Debye temperature, then this electron-phonon scattering rate goes as T to the power 5, right? So we have these 3 different types of scattering rate, and in this equation you can see it's kind of 1 by tau. So our simple assumption is that our 1 by tau is nothing but like the combination of all of them. So we have here electron interaction scattering rate, then we have electron-phonon scattering, and then we have electron with the impurities, right? So that's our assumption of the simple model. And in this equation you can replace 1 by tau with different terms here, right? And you can see this one goes as T square, this one goes as T to the power 5, this one is independent of temperature. So we have some term which is independent of temperature, we have some term which is T square, proportional to T square, and sometimes we have proportional to T5. So from that you can kind of see that the resistivity, right? If you write the resistivity, we have some terms that's independent of temperature, and let's denote that term by some fixed number rho naught, right? And then we have some terms that is proportional to the square of temperature, and let's say the proportionality constant is A, and we have some term AT square, and then we have some other contribution from electron phonon interaction, and which is proportional to the T to the power 5, and you can write them as some proportionality constant B times T to the power 5, and then if there are other scattering processes, you can consider them all, right? But the one good thing to remember is that if you look at this expression, if you put T, which is very small, right? If you decrease the T, it's saying that yes, rho is going to decrease because you are decreasing the T. But one thing to note is that when T is really very small, let's say around like the absolute zero, the resistivity will be a fixed number independent of temperature, right? And that was the expectation that Kamerlingh-Onnes have in this low temperature measurements, that it should saturate to some fixed value independent of temperature. But what really happened was really surprising and very shocking, that at below some temperature, which is Tc, the resistivity was exactly zero. And that was really puzzling, right? And just before I end this lecture, let me mention one thing, is that if you understand the level of complication for superconductivity, then you can appreciate the fact is that the superconductivity was invented by Kamerlingh-Onnes in 1911, right? And the microscopic theory that can explain superconductivity was like derived by Bardeen, Cooper, and Schrieffer in 1957. So you can understand why such a long time was required to fully understand this superconductivity, right? No one has any clue why at below certain temperature the material resistivity vanishes. And there are different proposals, many tried, many brilliant physicists like Feynman, Einstein, they tried, but none of them succeeded. And then in 1957, Bardeen, Cooper, and Schrieffer really give the macroscopic theory explaining why superconductivity occurs in some material, right? I think that's about it for this lecture, and thanks for listening.